The last motor that we'll talk about in this presentation is called the stepper motor. Now this is actually the baby of the motor family. It really didn't come on the scene until the early 60s as a replacement for expensive servo systems and computer peripheral equipment. There's a couple of things you'll notice that's different about a stepper motor compared to some of the other motors we've looked at today. First of all, the rotor is magnetized axially, not radially. So that's quite a change from all the motors we've talked about. It has a doubly salient design, and what that means is there's actually protruding structures on both the rotor and the stator. You can actually see the teeth that exist on both of those structures. Now, it's very popular with open loop position control systems. That's where the stepper motor really shines. If you want to just do some kind of position control without any kind of feedback, you just bang out a certain number of steps and the stepper motor theoretically will go to that position. And that's one of the things that makes this motor so attractive. Engineers choose this motor in their designs because they think it'll be a really easy motor to use for position control. And what they find is that this motor, because it is so underdamped, it wants to ring like a banshee if you don't control it exactly the way that it wants to be controlled. There's resonance problems, there's noise problems, and this may very well be your 3 a.m. wake-up call trying to figure out how you're going to get this motor to behave. So let's open up the stepper motor and see what's going on inside of here. So we're actually looking at the south end of the rotor at this point. And one thing you'll notice is that there's a different number of teeth between the rotor and the stator. In fact, if you go around the circumference of the machine 180 degrees, you'll find that the rotor has one more tooth than the stator does for every 180 degrees of circumference. So that means for a total of 360 degrees, in this case, the stator has 48 teeth, and the rotor actually has 50 teeth. So what we're going to do is let's turn on phase A as shown in this diagram. And when I do that, that means that the A phases or the A poles are going to have a north pole. They're going to create a north pole magnet in the air gap, and the A bar phases are going to create a south pole in the air gap. So that means that where the A phases are on the horizontal axis, we're going to get alignment of the teeth between the rotor and the stator. In other words, the south pole teeth on the rotor are actually attracted to the north pole teeth on the stator. But you'll notice on the vertical axis, that's where the A bar phases are, we get perfect repulsion between the south pole of the rotor and the south pole of the stator. So we have one axis of perfect alignment, which is caused by the attraction between the stator and the rotor, and then another axis of perfect unalignment due to the repulsion of the magnets between the stator and the rotor. Now let's turn phase A off and turn phase B on. And when we do this, we see that the effect that it has is to shift our axes counterclockwise by 45 degrees. So now the aligned axis is on the phase B poles and the unaligned axis is on the phase B bar poles. When we do this, that constitutes one whole step of this stepper motor. So by commutating the current out of coil A and putting it into coil B, in this particular motor, it results in 1.8 degrees of movement. Now we can actually get finer movement if we do a trick called half-stepping. And what that involves is when you turn phase B on, you don't turn phase A off. You actually leave it on. That will result in the axes moving counterclockwise by 22.5 degrees, which results in a step size of 0.9 degrees. So if we alternate back and forth between the full steps and the half steps, we do that at a very fast rate. That's how we can actually make the motor spin as seen in this animation. Let's take a look at some different ways that you can drive a stepper motor, and we'll start over with the left-hand diagram, which is the one-phase technique. Now with this technique, we're only going to turn one phase on at a time. So first we'll turn phase A on, and then turn phase B on, followed by A bar, and then B bar. So when we go through 360 electrical degrees here, we actually get 4 full steps out of this technique. Now this is not used very often because we're only using part of the stepper motor at any given time. We're only driving one phase at a time. You can actually get much better torque performance by using the technique in the center of the slide, which is a two-phase technique. And in this case, we always have 2 phases on at any given time. Now this doesn't give you any more resolution. When you go 360 degrees electrically in your waveforms, you still only get 4 steps per electrical cycle, but you do get much better torque performance. If you want more resolution, what you can do is actually bounce back and forth between these two techniques. That's shown on the right-hand side. That's the 1-2 phase technique. And here we have one phase on, followed by two phases, and then one phase, followed by two phases. And this will actually result in 8 steps per 360 electrical degrees. This is the half-stepping technique that we were talking about in the previous slide. Here we can see the space vector diagrams for the current vectors with each one of these techniques. Again, you can see that by going from a one-phase full-step drive to a two-phase full-step drive, I don't gain any more steps per electrical cycle. All I essentially do is shift my pattern by 45 electrical degrees. And then you have the half-stepping technique where I'm actually bouncing back and forth between one phase and two phase, and those patterns are essentially just overlaid on top of each other then to create the half-step pattern. But you'll notice that when I have two phases turned on versus a single phase turned on, I'm actually getting more torque out of the machine, and that's why those current vectors are longer. So that means when I'm actually bouncing back and forth between one phase being on and two phases being on, I'm actually creating a torque ripple on my motor, and that's an undesirable effect because that's going to probably stimulate one of the resonances inside of the machine. To get around that, I can employ some kind of current regulation technique using PWMs or some other modulation so that when I have both phases on at the same time, I'm actually reducing the length of that current vector. So that will give me much, much better torque performance. But then the question becomes, well, if I've already got some kind of current regulator in my system using PWM and I've already paid for that extra cost, then why stop at just 8 steps? Why not keep on going to more and more steps as shown in the examples of quarter stepping or micro stepping? Now when we get to micro stepping, you can probably imagine what those waveforms look like, and we'll show that on the next slide. Here you can see the current waveforms for a microstepped application, where each one of those little stair steps or little notches in the current waveform, that actually represents one microstep. If you plot the ideal position response of a microstep system versus a full step system, you can see why microstepping is so much better. You're actually imparting the same amount of energy to the motor with microstepping versus full stepping, but it's just that the microstep response is actually spread out much more evenly over the entire step versus the full step, where you're basically stimulating that system with all of that energy all at once, and as a result of that, it results in significant ringing and overshoot. Another thing that you should be aware of is that just because you're commanding all those beautiful microsteps to the motor doesn't mean that the motor's actually going to those positions. The waveform shown here would be the case of a perfect motor with no load. So with microstepping, you're not necessarily gaining position accuracy. What you're gaining is position resolution.